All right, let's just talk a little bit more about how to prevent overfitting. The way we do this is by using regularization. So one way of preventing overfitting is to gather more data. This is wrong, so this should be 2 and 3. We want to gather more data, and what we do then is basically we just go outside and collect more data samples. But this might actually not be possible. So this might be actually difficult. Collecting new samples is not always possible. Not always. Not always possible. And when the model is very complex, you might see that it actually needs a lot of data. So it's common to see that, again, the curve that I plotted before, capacity and data, is also sort of like exponential curve. So the more complex the model is, the more data you need. So for instance, convolutional neural networks, convnets, need lots of data because they are very complex models. Fortunately for convnets, we have very large data set of images, which is good. Another solution would be to do data augmentation. And you can think of having, again, a classification task. We want to classify images depending on what objects they show. And what you could do is basically maybe zoom in, or you could crop the image. You can also apply translations. So again, translate in the sense of like moving elements around, moving objects around. You can rotate the image. There's a series of transformations that you can apply in order to get new data from your existing data. But you should always make sure that the labels, after applying these transformations, the labels remain the same. So if I have, for instance, a classification task where I want to classify handwritten digits, and I have a 6, and then I apply a transformation to this 6, and I rotate this 6 maybe, then I might get a new sample that looks like this. But then now this sample is not a 6 anymore, it's a 9. So this shouldn't be allowed because now I changed my label. In practice, it's also good to first try simple models and then scale to more complex models if there is underfitting. So this is also known as the Occam's razor. Basically, you should prefer a simpler model before using a more complex model with many neural networks, because that's more prone to overfitting. So try simpler models. This is important. Okay. Other more sophisticated approaches to regularize our neural network and make sure that it doesn't overfit are parameter, norm, penalties, and dropouts. So let's start by explaining what the parameter, norm, penalty is. So if we have a loss function, let me just change the color maybe. If we have our loss function from before, and this is the 2 norm of y minus y hat, then we can add a new term to this loss function, which will be lambda times the 2 norm of our weights, w, and also take the 2 norm of this. And this is called L to normalization, regularization. Or also reach regression. So essentially what we see is that these are two competing losses, and if we have say a linear regression model like this, this is just to simplify. Neural network is not a linear regression, but it's sort of, the intuition is sort of equivalent. So we could have W1 times X plus W2 times X squared plus W3 times X cubed plus W4 times X to the power 4. And we were trying to fit, say, a data cloud again that looks like a parabola. These two error terms will be sort of competing against each other to try to fit this, this model to the data. So what you see is that this is trying to push the weights to be as small as possible, while this is trying to push the loss to be as small as possible. So this is two competing losses, and essentially what this means is basically that for this particular equation, for this particular model, we'll see that because just this one and this one are essential to fit a parabola, what we'll see is that these guys, W3 and W4, are pushed towards 0 because they are not necessary, and therefore if we push them towards 0, if we make them very small, then their contribution to this loss here will be also very small. And because they're not needed, they're not going to affect our loss. So this is actually good, right? Because now we remove these guys or make them very small, and then we simplify our model. So this was for linear regression, but it also applies to neural networks. And let me just draw a picture of how this looks like. So I can have, again, a loss function that looks like this. These are my contours. So each of the points at these curves have the same loss, this loss here, the same mean square error. And then I can also plot this guy here, and this will look something like this. So it's essentially like a paraboloid, like a parabola in 3 dimensions. This is W2 and W1. And so what you see is basically that these two competing losses are gonna find a trade-off. So if this is the optima, W, for this loss, these two competing strategies, these two competing losses will find a trade-off, which depends very much also on these values. So this basically tells us how much we care about regularizing, how much we care about making the loss small, the weights small, compared to how much we care about making the error small. So the point depends very much on this value. So you will see that basically the algorithm will stop when it finds this equilibrium point. Now there's another type of loss, another parameter norm penalty, which is called the L1 normalization or regularization, and this can be expressed as follows. So we have, again, our loss function, the 2 norm, and then we add an extra term, which is now the absolute value of the weights. And by the way, this norm here can be basically written like this, is W times W transpose. So W transpose times W. This is basically the square of, so this is essentially equal to the summation over all W's of W times W, and then this lambda here, W. So let me just I, all W's, Wi times Wi. Cool. Okay, so instead we have this guy here, which is also a summation, but without a square root. Without squaring the values. So we take the absolute value for each of the weights. Essentially, this can be written as follows. This is a summation of I equal to 1 to W, which is the number of weights. It's essentially the absolute value, of the weights. The summation of the absolute value of each of the weights times lambda. All right, and if we plot this, what we see is that my loss still looks like the previous one. My loss looks still like this. But now my regularization term, my penalty, looks like this. So each of these points at these different rotated squares take the same value or have the same L2 value. L1, sorry. So this is L1. Also known as lasso as well. Lasso. So each of the points in these contours that I'm writing in these squares contain the same value for the regularization term. And then what you see here is that basically, essentially what we see is that the intersection point between the intersection point between my loss, this guy here, and this guy here is going to be likely to be at one of the vertices, because these vertices will actually intersect before any of the edges with this curve. So it's very likely that the intersection happens here before it happens at any of these edges, which is good, right? Because that means that if the intersection, if the equilibrium point that we find is somewhere at each of these corners, then that means that one of the weights, if that is W1 and W2, will be essentially 0, which is actually pretty good, right? Because now we create this sparsity by just adding a penalty. And as you recall from previous lectures, the sparsity allows us to simplify the computations, because we need to compute the gradients, or we don't need to forward propagate through the neurons that are whose output is actually 0. So this is a bonus that we get, and what you see here is that these guys will basically, in the case of the L2 norm, this will be make very small, but not necessarily 0. In this case, it's likely that the weights will be pushed to be exactly 0, which is a bonus thing. Okay. And then the last regularization technique is called dropout. And the strategy is the following. You basically select at random what neurons to ignore to drop out when training. So perhaps you have a neural network like this. So we have these connections here, like so. And then we have 2 output neurons as well. So something like this. And eventually we decide that a particular time step, we decide a particular iteration, we decide that we are not going to use this neuron. This neuron is just ignored. So the output, we make the output 0 on purpose. So everything, we can only rely on this neuron now. So we do that for every layer. With a certain probability, we just drop out, the probability could be 0.5, we just drop out some of the neurons every time we do a new iteration, a new training step. And the reason we do this is that because there is a lot of neurons, they sometimes, when the model is too complex, they tend to compensate for their mistakes. They tend to co-adapt to each other. And by co-adapting, I mean compensate for their mistakes. So essentially, maybe just as an example, you could have a picture of a car with a number plate. A number plate could be 632 maybe. And maybe a neuron becomes very good because it has seen this car in many pictures. It becomes very good at detecting that there's, that a feature for detecting whether this is a car or not is by just reading these numbers and then realizing, okay, if this is 632, then this is a car. And this is actually not what we need, right? Because we humans, we don't really recognize that something whether something is a car by just looking at the numbers in the number plate. But a neuron, if the neural network is very complex, then it might memorize these numbers and decide whether something is a car based on that. And then it might output that something is not a car when the numbers are not there, which is not actually true. So what you see in practice is that this might actually happen, but then there is another neuron that compensates for this particular neuron by just saying, look, even if there's no 632, if the number plate is not 632, then this is still a car, right? And you're wrong. So maybe neurons compensate for each other's behavior. So a neuron can overfit to a particular sample, but maybe when it sees a new sample, it really outputs the wrong value. But there is another neuron farther in the neural network that compensates for that mistake. So this is what we are trying to prevent. We were trying to prevent neurons from co-adapting. And the way we do so is by not letting the neurons to rely on other neurons, right? So if this is my neuron now that is very good at recognizing a particular number plate, and then it outputs the label of car, or it outputs or recognizes the car only when it sees that number plate, and that neuron relies on this other neuron, which compensates for its mistakes. If this neuron is not always present, this neuron, the neuron that is left out, cannot rely on the other one, right? Because it doesn't really know whether this neuron is going to be there to fix their mistakes. So we remove this ability of co-adapting. And essentially what that means is that neurons do not overfeed anymore to our data, to our training samples. So this was just a more an intuitive explanation of dropout. And if you're interested about it, it's a cool topic. You can read the book, or there's also some blog posts that talk about it. But I'm not going to go into the math because it's a bit complex. Essentially, the intuition is that we're trying to prevent the neurons from overfitting to data. We're trying to prevent them from co-adapting to each other by not allowing them to rely on the others, by removing in some of the iterations the other neurons. Okay, so this was all for the regularization. And now I'm going to talk about the training loss, the loss function. And so it's common to apply this maximum likelihood estimation principle. What it says is essentially that if I have my weights, what I wanna obtain is the maximum, the argmax of the probability for each of the samples, for each of the data points in my data set, we want to maximize the probability of predicting the true label. And the true label for each of the samples is essentially yi. So I denotes a particular sample given xi and w. And I want to maximize this probability for each of the samples, and I know that the samples are independent, so essentially what I want to maximize is the product of these probabilities from I equals to 1 to m. So I want to maximize the probability of y1 given x1 and w times the probability of y2 given x2 and w, and so on. Now, working with products is not very convenient, mathematically speaking. So what we can do is we can apply a transformation to this. So we can have that the maximum likelihood estimate of the weights is given by the argmax of the summation of the logarithm of this probability here. Probability of yi given xi and w. And we're trying to maximize this instead, because you know that the log of a times b is equal to the log of a plus the log of b. So if we do this, if we apply the transformation, we just take the log of this, then essentially we get something like this. Summation from I equals to 1 to m. Okay, so that means that for a classification task, we essentially are trying to, instead of maximizing this, because we normally prefer to minimize, there's actually no reason, but it's easy to think about minimizing the error rather than maximizing the error. We have that this is 1 over m, so we take the mean over all our samples, if m is the number of samples, from I equals to 1, from I equals to 1 to m, the number of samples, of yi times the log of pi plus 1 minus yi, the label of that particular sample, times the log of 1 minus pi. And this is for the case when we have two classes. So you can see that this is essentially just the mean of this. So we want to maximize this guy here. We just change the sign. So instead of maximizing, we minimize. And to maximize this, we just need to maximize this to make these probabilities as large as possible. So essentially, this is what we see here. And then we just multiply by the label, because we have two classes. If the label is 1, then we will be looking at this probability, at the log probability. If the label is 0, then we'll be looking at this one. And we're just trying to maximize this to make this as large as possible. For a multi-class classification problem, we have a very similar equation, but now we need to sum over, not just over all our samples, but also over all our classes. C equals to 1 to k over all my classes. Because now, if you think about it, if I have 3 classes, I will have 3 outputs. yi, y1, y2, y3. So then I need to sum over all my classes, y, I, c, times the log of b, I, c. And essentially pi, c, and p and y hat are the same. So this is also y hat I, c. But because we're modeling probabilities, I just denote the output as p. And these two, so if this was, instead of n classes, this was 2 classes, then we could basically get this same expression by using the fact that the probability of one class is 1 minus the probability of the other class. So this is for n classes. And then basically you see that like we only pay attention to the output or the label that is 1, right? all this label, if this label is 1, then the probabilities that are predicted for this one, maybe 0.01 and 0.2, these are not taken into account when minimizing the loss. We only care about making this probability 0.8 or 0.79 in this case as large as possible, as close to 1 as possible. This is what we see in this expression here. Okay, and then for regression, one can prove that the maximum likelihood estimator is 1 over m of minus 1 over m of the weighted summation. No, sorry, I think in this case there's no minus here, because we're trying to minimize the loss. We can show that by applying the maximum likelihood estimation principle into a regression problem, you essentially get the mean square error. So the square error and then the mean for all our samples. So in practice, this is the function that we're trying to minimize. We get a data set, normally we split between training and testing, and then we try to minimize the training error. Okay, so let's just move on. Okay, so essentially we have two different ways of optimizing our neural network. The first one I'm going to discuss is a stochastic gradient descent. And what this guy does is just takes one sample at a time in every iteration. Maybe I'll change these colors because maybe this is not easy to see. So I have one sample, and I use that sample to estimate my gradient. Because as I mentioned at the beginning, I don't know the true loss, so I cannot just take the gradient and then set it equal to 0. I need to estimate my gradient. And there are a few problems with just using... let me just first talk about the advantages. So using one sample is easy because I get... so it's easy to compute and it's fast. So fast computation. So I essentially just need to forward propagate that sample, calculate the error, and then use that error to update my using the gradient analytical expressions that we have from the backpropagation algorithm. Can calculate the gradients, I can estimate the gradients based on that error, and then update my weights. So this is fast to compute, but the problem is that this is high variance. And essentially what that means is that, because when you compute the probability or the mean of a data set, when you have a data set x1, x2, x3, and you want to compute the mean of these values, the more values you have, the closer you'll be to the true mean of this data generating distribution. So here is the same. The more samples you have, the more samples you use to compute the estimate of the gradient, the less variance, the closer to the actual mean it will be. So this has both advantages and disadvantages. Let me just talk about the main disadvantages. This might mean slow convergence. And the reason is that because there is a lot of noise in this gradient estimation, high variance for the gradients, there's a lot of noise. If I plot the training loss, it might look something like this. It might go up and down a lot because these estimates are not actually very accurate because they're just based on one sample. So slow convergence is one problem. Another problem could be that because of this stochasticity, because of this noise in the gradient calculation, we might skip our global optima. So we might find the global optima, and then for some reason, if we are somewhere here, maybe we just jump away of that local optima and end up in a... We jump away from the global optima and end up in a local optima. So move away from global optimum. Okay, but then on the other hand, this could actually be helpful, the fact that it's stochastic, because that may allow us to also jump and also avoid local optima for the same reason, right? Because we, instead of getting stuck here, we might just jump away from it and then find the global optima. So it can be good or bad. It doesn't need to be necessarily bad to have this stochasticity. On the other hand, on the other end, we have, so this is one end, and the other end we have batch gradient descent. And in batch gradient descent, we use the entire data set, m samples, at every time step to compute the gradient. So this is obviously slow computation, because now you need to actually forward propagate all the samples, compute their errors, and calculate the gradients using those errors. And this might take forever, especially if we have a very large data set. But then the good thing is that we get a very low variance estimate, gradient estimate, gradient estimate. And this is actually good, right? Because now instead of having a slow convergence like before, the convergence is less noisy, so it converges faster, fast convergence. Now we might need fewer steps to converge to the solution because our curve or training will be much more smooth. Sorry about that. Okay, so then another issue that we might face is that, now, now instead of being able to jump away from local optima, we might get stuck on a local optima. So we might get stuck here because now you don't have that property of a stochasticity in your steps, so you might get stuck here in the local optima, which is not good, right? So fast convergence was good, but then getting stuck in a local optima might be bad. And then slow computation, that's bad. So in practice, what we want to find is a trade-off between the two, and this is known as mini-batch gradient descent. A mini-batch gradient descent is basically, as you can guess, instead of taking either one sample or the entire data set, is just choosing a size for that batch and then using that to estimate, using a few samples to estimate the gradient. So first, the good thing is that you get a low variance estimate, or at least a lower variance estimate than using a stochastic gradient descent. And then you can also compute that gradient faster. So fast computation. And this is normally what people do in practice. Mini-batch gradient descent. The only or drawback is that we have a new hyperparameter that we need to tune, which is the size of the batch, or maybe batch size. And this needs to be tuned. Okay, all right, so this is just the final slide. So hyperparameter tuning, this is an important thing in when training neural networks. So we just discussed one hyperparameter, the batch size, but there are many others. So one could be the number of neurons, the number of layers maybe, the learning rate that we know about, rate, and maybe batch size as well, batch size. So this is just a few of them, and normally what you do is you could do some sort of like grid search to find the right configuration. So you could have your train set, X train, Y train, and then you could have your test set, X test, Y test, and then you could use basically the test set to choose the right hyperparameters, right? So you first choose one. You first start with a particular configuration, say, I don't know, like 10 neurons, 3 layers, alpha equals to maybe 0.01, and the batch size is 32, just as an example. And then you evaluate that on your test set. You get a score, and then you try another configuration, you get another score, and you decide the one that is actually the best based on these scores. However, this is actually not good, because then what you're doing is you're actually overfitting to your test set. You're choosing the actual configuration that is best for this particular test set. So when you give the performance of your model, this is not the true performance, right? Because you chose the right hyperparameters that are best for this test set, but this might not be the best for the data in general, right? For my data generating process. So essentially what is done is we need to have another subset, which we call the validation set. And I'm just gonna, so we need another subset of my data set, which is known as validation set. So now we're splitting the data set in 3 parts, in 3 partitions. And this actually, if we don't have enough data, this might actually be bad, because then the training set might be too small for training a neural network. And the fact that we need to also have some subset, or we need to leave out some subset of samples in order to first find the right configuration, and then report the score or the performance on the test set. If we don't have enough data, this might not be very efficient, but there's a way to solve this, and it's known as cross-validation. So cross-validation works as follows. So the idea is that we want to use all our data for training our model. And the way you do this is essentially you first divide your data, you split your data in, say, like 5 different subsets. This could be 5 or could be 10. This is another thing you need to discuss, or you need to actually choose based on the amount of samples that you have. For this particular case, we're just going to split our data in 5 subsets. And then you do sort of like an iterative process. So the first iteration, you basically choose from these subsets, you choose 4 of them. So maybe these 4. And you train your model using these 4. And then you use this one for testing. And then maybe in the second iteration, you then change, and instead of using these 4 here, you use maybe the first one, and then you leave the second one out, and then you use these 3 here. So you use this for test, and the rest is training. So in every iteration, you will be getting a score or a performance, the loss the loss. This score is the loss. Score 2. And essentially what you do after trying all the different configurations for my subsets, so 3, in this case there will be 5 different configurations, 3, 4, and 5, then you get 5 scores, and then you take the mean of those scores, and essentially this is the mean, this is the value that you report as your generalization error, as your test set error. And this allows you to actually use all your data for training your model, which is good, right? Okay, so in practice, because we also have the validation set, what you could see is that maybe some people, what they do is if they have a data set like this, then they might leave out the test set. They just don't use it anymore, and then they take this and do cross-validation to choose to do hyperparameter tuning. So they just do cross-validation on this part here. So they split, say, in 5 parts the train set to do cross-validation and to do hyper tuning. So they use cross-validation for hyperparameter tuning. Another way would be to basically have 2 nested loops. In the first outer loop, you do cross-validation for reporting the test error, and in the inner loop, you do cross-validation to do hyperparameter tuning. And this is a way of using the data, or using as much as possible of your data, but it's also less efficient, right? Because now you have like 2 loops and you need to train many different models. It can get very inefficient, especially if you have a very large data set. But these techniques are normally applied to small data sets when you don't have enough samples. You have like 2 million images, then using cross-validation is not that necessary, because you can just leave out a set for validation and a set for testing, and then train on the other subset of samples. All right, so this was all for today. You can email me or send me your questions using comments to this YouTube video, and I'll try to answer all of them the best I can. Thank you very much for listening, and I see you on Wednesday.